Hi everyone, this is Miss Lasar, and today I'm going to be teaching you about renewable energy. Last week was non-renewable. Now we're on to the good stuff. Okay, here's our table of contents. I'll be teaching you about solar energy, wind energy, hydropower energy, geothermal energy, biomass energy, hydrogen fuel cells, and then cogeneration and energy sustainability. You know the deal. Make sure you're taking amazing handwritten notes during this lecture. I will definitely be talking faster than you can write, so get ready to pause the video when you need to copy down everything that I put on the screen into your notebook. Okay, let's get started with solar energy. So solar energy actually comes in three flavors. The first flavor that we're going to talk about is passive solar heating. Remember, when I say solar energy, I'm not just talking about the energy that comes from the sun. I'm talking about how we use that energy in the sun to do things for us, like heat our buildings. So passive solar heating is when heat is directly absorbed from the sun without mechanical or electrical equipment. Take a look at what I mean by that in this image. Notice that this house has been especially built so that during the winter, when the sun is lower in the sky, the angle of the sun goes straight in through these super windows that are also triple layered for extra good insulation. It's absorbed, and there's heavy insulation that keeps in that heat that's generated. But during the summer, this building has been built so that the high summer sun is blocked by the angle of the roof, and the house is shaded from that. This house really takes into account all of the different building mechanisms that need to be put in place for effective passive solar heating. We've got triple thick windows, we've got heavy insulation, we've got a vent that can open in the summer so that extra hot air can rise and escape through the roof. We've got a white or light colored roof to prevent overheating. We've got a stone floor and wall for heat storage. This house has been built very particularly. So this is an inexpensive and low maintenance way to take advantage of solar energy. But it's really difficult to retrofit. If you want a house that's passive solar, you got to build it with that in mind from the beginning. We can't take our existing houses and retrofit them to take advantage of passive solar heating. We also can't store energy. There's no way, there's no battery system, there's no energy storage system besides just the floor and the wall absorbing some heat energy and radiating it later. This is our second type of solar energy, active solar heating. So this will be a little bit of a technological upgrade from passive solar heating. Here we're using mechanical and electrical equipment to transfer solar heated liquid to transfer heat or create electricity. Take a look at how this is set up in this house. So first thing to notice is that there's a solar collector on the roof, and we've got water that's being piped into the solar collector. That water is being heated up by the sun during the daytime. And then there's a pump that will bring that heated water into the house, and a heat exchanger will allow us to transfer the heat from that water from the pump into the pipes in our house. And we can use radiators to radiate that heat throughout the house. And then that water will be mechanically pumped back up to the solar collector to be recharged with some more heat energy. So notice that unlike passive solar, where we didn't really need to put in any electricity at all, we just needed to put in the effort to build our house properly to take advantage of solar energy. Here we are continually putting in a little bit of electricity in our heat pump. So this can generate heat. It can also generate electricity if we can get our water hot enough to boil. This has both large and small scale applications. We could have a solar heat pump for just one house. We could have one for an entire apartment complex. We can change the scale of it. But it's expensive, and it requires significant maintenance. Here's an example of a passive solar house in Colorado. Notice here we've got a super-sized window with a large overhang to block the sun during the summer. We've got a variety of techniques to keep this house cool in summer and warm in winter without putting in any extra electricity. Here is a large array of rooftop solar hot water heaters in apartment buildings in China. They're actually now required on all new buildings in China. And so you can see it looks like solar panels. These are not solar panels. These are just solar hot water heaters. So speaking of solar panels, when I said we're learning about solar energy, you probably didn't think about either active or passive solar heating. You probably thought about Photovoltaic cells. These cells that can transform sunlight directly into electricity. And so that's obviously a really important thing to talk about when it comes to solar energy, how we can use it to generate electricity. So here is our actual schematic of a photovoltaic cell. There are three crucial layers. We've got our negatively charged layer, our positively charged layer, and our interior layer. That's a semiconductor material, usually silicon-based. And when sunlight hits the solar panel, it'll actually knock free some electrons from inside the semiconductor layer. They'll be knocked up, they'll move through this top layer, and then will be returned back down to this bottom layer, or will come in from the environment and be returned to this bottom layer to fill the holes filled by those free electrons. Remember that moving electrons, moving electrical charge, that is electricity. And so that's very roughly how solar panels will be able to transfer energy from the sun into electricity directly. Okay, pros and cons of photovoltaic energy. Notice we've got many different size arrays. Right here, you've got two pictures of kind of residential building size arrays, but you've also probably seen solar farms, even out here on like the eastern shore of Maryland. There's many, many fields that have been covered in solar panels. So we can put solar panels on top of buildings, we can put them out in fields, we can put them across the desert, and that will contribute to our pros and our cons. So our pros. There are no direct greenhouse gas emissions from generating electricity using a solar panel. We aren't burning anything. There are no direct air pollution emissions at all when we're just looking at our operational solar panel. There's high potential for electricity generation if we can manage to harness a larger percentage of the sun's output. The sun outputs far more energy than we would actually need to supply electricity to all humans currently on Earth and to all industrial processes. So there's actually massive potential to supply all of our electricity needs with solar energy. The potential is almost anywhere. Virtually everywhere on Earth gets sunlight for all or for part of the year. We've got huge potential globally, and we can have large or small scale applications. Think about the small scale. This solar panel array might just be providing electricity to this house. These larger arrays might be providing electricity to this large school complex. We can have even larger arrays that are supplying electricity to a town. And it's economically beneficial in the long term. But what about the cons? At a really high upfront cost. Solar panels do not come cheap. If you and your family have ever discussed investing in solar panels, you might know that it comes with a large initial investment, and the cells themselves actually have a fairly limited lifespan. Most photovoltaic cells last for about 20 to 30 years. Think about what that means for how often we need to mine more non-renewable resources to actually build these photovoltaic cells, and also what it means for the frequency that we need to put in that large financial investment. They can be unreliable. Specifically, if the sun isn't shining, they won't be making any electricity, and we need a backup power source. They don't work at night, and there's no way to store excess power generated. This bullet point is actually changing right now. You might have heard that there are various companies, including Tesla, that are working on battery systems that can hook into residential solar panels and can actually store some of that electricity for later. But that's a fairly new technology. It's not widespread yet, and it's not large scale yet either. These large farms, you can see a large solar farm out in the desert down here, they use a ton of space and they can negatively impact habitat, especially fragile desert ecosystems. Desert ecosystems are particularly vulnerable to change because things just don't grow there very quickly. There's not enough water. So if something's messing with that ecosystem, it can have immediate effects and effects that are hard to overcome. Desert ecosystems are not very resilient. Finally, although the actual action of the solar panel itself doesn't generate any greenhouse gases, we're not burning anything, we got to think about the solar panel construction. All of these materials are non-renewable. We've got glass, we've got silicon, we've got aluminum frames. There's some other materials, minerals that are needed for building these photovoltaic cells, and Those are in fixed supply. How do we get those? Mining. What are we doing during mining? Removing the overburden, burning a lot of fossil fuels to power our equipment. So there's not a zero cost to generating these photovoltaic cells. And combined with their slightly limited lifespan, 20 to 30 years, a lot of these materials are not well recycled after those 20 to 30 years, and we need to go mine more. So there is a set of environmental issues around photovoltaic cells. Here's our photovoltaic power potential worldwide. So who's got the capacity to generate the most photovoltaic power in kilowatt hours over the world? And one thing you might be surprised by is how the equator right here actually doesn't have the highest photovoltaic power potential. Think about why. What's the weather like at the equator? It's our lowest pressure zone. We have a ton of precipitation. There are many, many rainy days when the sun is not shining. And so our desert ecosystems, 30 degrees north, 30 degrees south, they're going to have higher power potential because they're going to have fewer rainy days, more days when the sun is shining. And they're also going to have really high insolation, very, very straight up and down angles of incidence. What I'm trying to say is the sun will be high in the sky, and there will be a lot of energy in all of those rays of light coming in from the sun compared to our areas further north and further south, where the sun is at more of an angle in the sky and is lower power because of it. Next type of energy is wind energy. So how do we transform the energy from wind into electricity? We use a wind turbine. You're familiar with these. You've seen these around us locally. You've seen pictures of these globally. Here's the energy transformation process. The kinetic energy of moving air hits these blades. They spin. And so that kinetic energy of moving air is transformed into the kinetic energy of the spinning turbine. And that spinning turbine will spin a generator, so the energy will be transferred into our spinning generator, still kinetic energy. But we know that there is a magnet and wire or magnet and coil situation inside of our generator. And so as we spin those magnets around that wire, the kinetic energy of the spinning generator will be transformed into electricity. And that's how we make electricity from wind power. Let's talk about pros and cons. First, just notice the size of these wind turbines. Sometimes it's hard to think about the scale of them. Here's one of the newest types of wind turbines. Notice that it's almost as tall as the Eiffel Tower. Our average onshore wind turbines in the US are about half the height of the Eiffel Tower, taller than the Statue of Liberty. That's really tall. And our offshore wind turbines tend to be a little bit taller just because they can be, and they're a little bit more than half the height of the Eiffel Tower. So pretty darn tall. Pros of wind turbine energy. Super renewable energy source. When we think about how long this energy source is going to be around, it's not just a renewable energy source, it's a perpetual energy source. And come to think of it, we should probably add that to our solar energy pros as well. Pause the video, add that to your solar energy pros. Thank you. No direct greenhouse gas emissions. Same deal as solar energy. We are not burning anything. We're not generating any carbon dioxide. No direct air pollutant emissions at all. You probably know where I'm going to take this in the cons. You've probably already thought about it, but we're not burning anything with these wind turbines themselves. We are not directly emitting any greenhouse gases or other air pollutants. And it will lower energy cost in the long term. So we'll talk about why I say that in the cons, but these wind turbines can be quite expensive. They do have a fairly long lifespan, and so although they will have a heavy initial investment, they will lower energy costs in the long term. They also have very high potential, especially offshore. We've got a ton of spaces on Earth that are ripe for wind turbine expansion. What about cons? High upfront costs. These wind turbines, think about building the Statue of Liberty. These are not small things that we're creating, and we are proposing to build quite a few of them. That is a large upfront cost for materials, for installation, etc. And like solar energy, they're unreliable in that when the wind isn't blowing, a backup energy source is needed. Some areas don't have suitable sites. There are some areas on Earth where there's just not enough wind, but also think about like a tropical rainforest. How are you going to build a wind turbine in a tropical rainforest? You're going to be disturbing a lot of habitat space. We just don't do that. It's too difficult to get materials in there. There's too much of a risk for the wind turbine to be messed with. We don't build wind turbines in forests. We don't build wind turbines in tropical rainforests. We tend to build them in flatter habitat areas like prairies, like grasslands, and offshore. Wind turbines can kill birds and bats. This is probably the area where wind turbines get the most negative press, and it's kind of hilarious because this is such an overstated con. So here's a little bit of data about who's killing birds in the United States. Notice that cats kill over 2 billion birds per year. Collisions with building glass kills almost 600 million birds per year, and collisions with wind turbines kills about 200,000 birds per year. Yeah, 200,000 birds is not insignificant, but compared to these other sources of bird death, it is just laughable to say that this is the major con with wind turbines. Additionally, there was some new research that came out that showed that if you just paint one of the turbines black, it significantly reduces bird deaths by up to 70%. So we can continue to cut down that number. Like solar energy, there is currently no way to store excess power that's generated, although that is definitely an area that it seems like we're making some major technological improvements in. And another big con of wind turbines, people think they're ugly, and so they can lower property values. And so where will we build wind turbines? Not around areas where there are wealthy people that can lobby to have them not disturb their pristine views and landscape. Wind power availability. Here's a map of the United States where we've indicated the potential for wind power from fair, which is in orange, all the way to superb, which is in blue. Notice that there are some offshore regions that are noted as well. If it's in white, that's an area that we don't think is suitable for wind power generation, either because there's not enough wind there on a normal basis, or because, like in the southeast region of the United States, we've got hurricanes. In some of this mid-Atlantic region, it's just too forested, similar up here. So there are some regions, especially offshore, where we have some outstanding or superb areas for wind generation, and those are regions where we'll definitely look into the potential of building more wind turbines. Hydropower energy. Okay, how do we take the flow of moving water and turn it into electricity? Well, here's our chain of events. Notice that this is a hydroelectric dam that you're looking at here, and you can probably already infer what's going to happen just by looking at these pieces. In hydropower dams, we take the kinetic energy of moving water, it's flowing downhill, and that is converted into the kinetic energy of spinning a turbine, right? Because it's flowing, spins that turbine. Then that is transformed into the kinetic energy of our spinning generator, and we've got our magnet wire situation, and that is how we will generate our electricity. Here goes out to the power grid. You actually already know a lot about this already and where I'm going to go next with the pros and cons, because we've talked about dams multiple times already. So a lot of this will be review. Pros of hydropower: no air pollution once the dam is installed. Again, just like solar and wind energy, we're not burning anything. No waste once the dam is installed. Relatively inexpensive once the dam is installed. And our reservoir provides additional services, all of those recreation things that we can do in our reservoir. It prevents downstream flooding. That's one reason that dams get installed in the first place, let alone hydropower dams or hydroelectric dams. And it's a very reliable energy source. It is not particularly weather dependent. If there is a drought, we might have lower water levels than normal, but that type of large-scale climate change would indicate that it's a river that's not suitable for building a hydroelectric dam on. We would only build a hydroelectric dam on a river that has very consistent high levels of water flow. And our single source can generate huge amounts of electricity. Whereas one wind turbine actually does not generate all that much electricity, one hydroelectric dam can generate enough electricity to power a decent chunk of a town or small city. Cons. You've seen these cons before. Methane emissions. Where do they come from? Organic matter anaerobically decomposes at the bottom of the reservoir in an anoxic environment. We get all that sediment buildup back here. It decomposes, releases methane. Upstream flooding. There's intentional flooding when we make that reservoir happen. But we're going to be flooding natural habitat, and we're going to be displacing anybody who lives in those regions. High upfront cost. How are we going to afford this? Disruption of fish migration. Poor salmon migration in the Pacific Northwest. 90% of the salmon populations have been decimated by the presence of dams in the Columbia River Basin. Reduction in nutrient-rich sediment to downstream estuaries. We know it's going to get blocked behind this dam wall. It's not going to be able to flow downstream. We may actually see estuary loss, wetland loss, as there's just not enough sediment, not enough stuff to support those physical landscapes. And interestingly, most viable sites are already in use. Let me show you a map of hydropower around the world. Take a look at the world's rivers. Rivers in blue are not yet dammed. They are free-flowing. Rivers in red are significantly dammed, and rivers in green are a little bit dammed, but still have pretty good river flow. Over half of the world's rivers have already been dammed, and most of the undammed rivers are undammed because they may not have super reliable water flow. Advancements in hydroelectricity. Okay, there's other ways to generate electricity from moving water besides damming a river. Two in particular that are interesting to know about: tidal energy and wave energy. Okay, so here's my tidal energy diagram. Notice that we have what is essentially a dam. This would be at the entrance to like our estuary. So think about a giant dam at the entrance to the Chesapeake Bay. And as the tide is rising, these gates are actually up, and water will be flowing in. The tide will rise, and eventually we'll have our high tide level where the ocean is high, the estuary is high. And then at that point, when we're at high tide, we'll actually close these gates. And then our ocean water will recede. But because we've closed these gates, we have a whole lot of water backed up right here behind our wall. And then when we're at low tide, when our ocean is at its lowest level, we will open up these gates and water will rush out in a big flow, and it will spin this turbine, which you know is attached to a generator, and will generate electricity that way. Wave energy is a much smaller scale effort, but harnessing wave energy involves using small devices that can transform the bobbing motion of the ocean, use that to spin a turbine and generate electricity. Pros and cons. The biggest issue right now is that both of these have relatively low energy production, and they have very high maintenance costs because they're both operating in saltwater. And you've learned this before, saltwater is really corrosive, which is why we use only freshwater in industry, one of the major drains on our freshwater reserves. Next type of energy to talk about is geothermal energy. And you might be surprised to learn that while we think about geothermal energy being crucial in places like Iceland, we actually use geothermal energy to provide heating to a number of MCPS middle schools. Fun fact. Here's how geothermal energy works. We pump cool water down an injection well. So this is water that we've harvested from our freshwater resources. We pump it down low enough so that stored heat from the Earth's interior turns the water into steam. And you know what that steam's going to do. Steam rises from the production well. It turns a turbine, which turns a generator, which produces electricity. So let's talk about pros and cons of this process. Pros: no greenhouse gas emissions. We're not burning anything. No air pollution emissions at all, usually. We'll put an asterisk next to this because although we're not burning anything, we'll talk about on the next slide, there is one particular type of air pollutant that may actually be emitted. Very reliable. Geothermal energy is not at all weather dependent. Doesn't really matter what's happening up on the surface. The Earth's core is still going to be hot and heating up our water deep underground. It's relatively inexpensive to operate a geothermal plant. And now the cons. Okay, so this is a geothermal plant in Iceland. You can actually see in front of it some parts, some like edge parts of what's called the Blue Lagoon. These are natural hot springs that are also heated by the same geothermal energy that's being used to create electricity here at the power plant. All this steam that's rising, that kind of freaks people out, right? They're like, oh, look at all that smoke. That's not smoke, that's steam. Remember, that's steam that we couldn't condense back down quickly enough, and so we just release it from our cooling towers. Cons of geothermal energy. Its accessibility at a reasonable cost is limited. Think about where on Earth it gets really hot near the surface. You might have seen cool videos of people baking cakes in the superheated sand in Iceland. Iceland is one region that people always talk about because it's by a tectonic plate boundary, a divergent tectonic plate boundary. And so we know we've got magma close to the surface there. But for many other regions on Earth where you're not close to a tectonic plate boundary, magma is pretty far away from you. And you have to go down very, very, very far to find a layer of crust that's hot enough to warm up your water or turn it into steam. And so, while technically we could just drill down anywhere on Earth and pump our water deep down, it'll be heated up and turned into steam. In most places on Earth, we have to drill down so far that the cost becomes prohibitive. And there's few regions on Earth where there's really magma close enough to the surface for us to take advantage of here. And we do release some gases, especially during the drilling process. While we're drilling new geothermal plants, we tend to release hydrogen sulfide gas. If you've ever been to a natural hot spring, you know that sometimes natural hot springs have the smell of like rotten eggs. That's hydrogen sulfide gas that you're smelling. And released in large quantities, that can be an air pollutant. You'll learn in our next unit what the issues with hydrogen sulfide gas are. This is not released in particularly high quantities at geothermal plants, but it is something to think about. The drilling itself can cause earthquakes. There's actually a lot of similarities between this process and the process that we think about when we talk about fracking. So in fracking, we're also injecting water deep underground. And remember, that has the ability to destabilize rock layers and cause earthquakes. If we're causing earthquakes, if we're destabilizing our rock layers in a region close to groundwater, there is a chance that we can infiltrate our groundwater resources or that we can impact them. Maybe we mess with which areas are permeable and impermeable. We could potentially contaminate some of our groundwater if we're injecting impure water. We may just be exposing one rock layer that has, I don't know, slightly radioactive minerals in it to our groundwater layer that didn't previously have radioactive minerals in it. There's all sorts of impacts on groundwater that we can make just from this process of injecting water and drilling deep underground, similar to what happens when we think about fracking. So these are geothermal heat pumps. This is a kind of, I would say, a less serious version of geothermal energy. We're not generating electricity here. We're just taking advantage of the temperature of the earth for either heating or cooling purposes. In the winter, we might pump out cold water from the house deep underground. It gets warmed up, and then we pump it back into the house. We might, in the summer, pump out warm water from the house, and in the summer it might actually be cooler underground than on the surface, and so that might cool our water down, and then we can pump it back up into the house. Notice in both of these cases and in our geothermal plant, we do need to spend some electricity just moving the water. These heat pumps, this is actually what we see at a couple Montgomery County schools. Geothermal availability. This isn't a totally comprehensive map, but this actually looks at the maximum aquifer temperature in various regions around the world, just to give you a sense of where we might have warmer temperatures. And actually, they get quite warm. So this is in Celsius. Remember, water boils at 100 degrees Celsius. So anything in this dark orange, like pinkish guy or dark pink guy, those are all well above boiling temperature. And notice that we have quite a few hotspots around the world. And so there is some possibility of expanding our geothermal energy production. Our next type of energy is biomass energy. And when I say biomass, I mean plants and animals that ate those plants. Biomass energy is energy that was stored during photosynthesis. So the chemical energy stored in plants or stored in plants that have been decomposed into peat, which is what you see here. And the first question when it comes to biomass energy is, well, we're going to burn stuff. What are we burning? We are going to be burning wood, peat, charcoal, dried dung, manure, I put charcoal on there twice, crop residue, like these leftover corn stalks, or even garbage. Peat might be a new word for you. Peat is this stuff. It is partially decomposed organic material. Peat bogs are wetlands that are filled with these thick layers of partially decomposed organic material. It's like pre-soil. There's a ton of carbon that's trapped in here. And when it comes to biomass energy, we are going to be burning all of these things. And we might be burning them to directly produce heat, or we might be burning them in a power plant to produce electricity. Biomass energy is the leading source of renewable energy worldwide because of its heavy use in LEDCs. In LEDCs, biomass energy is frequently used as a direct heat source. So when I say direct heat source, I'm thinking about heating a home, and I'm thinking about providing heat for cooking. In MEDCs, we tend to use electricity and oil for heating homes, and we tend to use electricity and natural gas for cooking. Biomass pros and cons. Okay, so notice this is actually an example of where you might see biomass energy heating a home in an MEDC or LEDC. This is a wood-fired stove. And so we put our wood in there, we burn it, and that hot air circulates throughout the house and warms us up. Here is biomass energy. Again, I think this is wood in this wood-fired stove being used for direct heat for cooking. Pros of biomass energy is that it's easily accessible. These things that we burn, these plant residues of a lot of varieties, are everywhere on Earth. It's relatively inexpensive. You can go gather your own biomass energy. You don't need any special equipment for it. It can be used for heating and for cooking, and it's carbon neutral if the rate of plant harvest is the same as the rate of plant new growth, or the rate of carbon dioxide production from burning all that biomass is the same as the rate of carbon dioxide absorption through photosynthesis. So this is kind of a tricky one. If we are burning our wood faster than we are growing new wood, that would not be carbon neutral. But some people do call biomass energy a carbon neutral energy source, because the argument goes, well, we already removed this carbon dioxide from the atmosphere in photosynthesis, so putting it back into the atmosphere does not actually count as putting more carbon dioxide into the atmosphere. You can decide what you think of that. Cons: air pollution is the biggest issue. Biomass burning releases significant amounts of air pollutants. So take a look at this indoor cook stove that's fed by wood. Carbon dioxide counts as an air pollutant, but carbon monoxide, CO, that's a potent indoor air pollutant. When it builds up in confined spaces, it can be deadly. Nitrogen oxides, which are lung irritants, particulate matter, which can get stuck in your lungs and it can actually enter your bloodstream as well, and volatile organic compounds, which can be carcinogenic, can be irritants, and can have other interesting health effects. Notice that when you're burning biomass, especially indoors, you're generating a lot of that smoke. You're generating a lot of those air pollutants indoors in a confined space where there's not a lot of room for them to be dispersed. Biomass is typically burned indoors, which intensifies the health effects of the pollutants. And over-harvesting trees for fuel wood results in deforestation. As a result of deforestation, we have soil erosion. Deforestation reduces the amounts of precipitation and reduces the amount of carbon dioxide sequestration. There are other issues with deforestation. You know this, you've heard these before. Connect that back to prior units. Biofuel is another type of renewable energy, slightly different from biomass. Biofuels are liquid fuels made from plant matter that can be used as substitutes for conventional petroleum products like gasoline and diesel. There's two in particular. Ethanol can be made as a biofuel, and it's made by fermenting plant-based starches. We can mix biofuel ethanol, which is indistinguishable from normal ethanol. We can mix it with gasoline up to 10%. And we can extract it from different plant sources: corn and sugar beets, which we grow in the US, sugar cane and sugar beets, which we grow in the Brazil. Those are the top sources of plant and starch material that we use to generate biofuel ethanol. The other type of biofuel that we really talk about is biodiesel. And again, this is mostly indistinguishable from diesel that's generated from petroleum products. This is extracted and chemically modified oil from plants. It can be a direct substitute for diesel fuel. And where do we get it from? Soybeans from Brazil and the US, from oil palms that you can see here in Southeast Asia, and rapeseed, which is what we call the seed that we use to generate canola oil, frequently grown in Europe. Let's talk about the pros and cons of biofuel. Just like biomass, we're burning it, and so we can consider it carbon neutral if the rate of combustion is the same or less than the rate of carbon capture through photosynthesis. So we're definitely more removed from photosynthesis in this case. We're not just growing our plants and then burning the leftovers. We're growing our plants, we're processing our plants, we're refining those extracts, and then we're eventually transforming it into biodiesel or ethanol and then combusting it inside of our vehicles. So if our rate of photosynthesis is the same as or less than our rate of combustion, we can consider it carbon neutral. And we can produce this domestically. This would vastly expand our own fuel supplies here in the United States. What about cons? Has a really low net energy. Gasoline and ethanol, actually, the gasoline ethanol mix provides fewer miles per gallon than just straight gasoline that you would put in your car. And so we don't get a ton of efficient energy out of our ethanol. Our biodiesel does have pretty high efficiency, but we spend so much energy processing the plant material to make it that we waste a lot of energy in the process, and it lowers the net energy. When we use cropland to grow things that can be used for biofuel, we might need to convert those agricultural grazing lands, those lands where we would be growing corn or other things for human consumption, to biofuel land. This is going to be monoculture. You know what's going to happen next. We'll have soil degradation issues. We might have food security and rising food price issues if we're lessening how much crops we're growing for human consumption. If we're converting our forest into biofuel land, then we're going to have all the issues with deforestation. Advancements in biofuel. One of the most promising ethanol advancements is making ethanol from switchgrass, which is a very, very, very fast-growing grass that requires very few inputs from us, much, much easier to raise than corn and some of the other crops that are currently used for ethanol production. We also are working on generating biodiesel from algae. And so we can actually make bioethanol or biodiesel from algae, but it's most promising as a biodiesel substrate. Again, easier to grow than a lot of the other crops that we're currently using for biodiesel formation. Okay, we're almost there, peeps. Hydrogen fuel cells. What the heck is going on here? Okay, so this is a hydrogen fuel cell. We're going to be generating electricity in this hydrogen fuel cell, and the process is a lot like a typical battery. A chemical reaction occurs inside the cell to generate an electric current, and that electric current, that is our electricity. It does have upgrades to a typical battery. The reactants can be continuously added. The fuel cell doesn't ever go dead. And hydrogen fuel cells will combine hydrogen gas and oxygen gas to create electricity. Here's how that happens. I'm going to read a little script that I prepared because this is something that's really not my area of expertise. The hydrogen fuel, H2, is added to the cell in this first reaction layer. It can be added in liquid or in gas form. And in the first reaction layer, the hydrogen molecules are split into protons and electrons. The protons and electrons will take different paths. The protons will move across the membrane. but the electrons are free to take an alternate route, moving electrons. That's a flow of electric current. That's our electricity. In the second reaction layer, we're basically dealing with these electrons and these protons. Oxygen molecules are going in, and they are split. They will combine with the protons and electrons, and they will form water. So water vapor is the only emission from the fuel cell. Pros and cons? Pros, water vapor is the only emission from the fuel cell. No air pollutants. We're not burning anything. No greenhouse gas emissions. No direct CO2 emissions. Very high electricity efficiency. We can convert a significant amount of the chemical energy in those hydrogen molecules into electricity. Hydrogen is the most abundant element in the universe, which should indicate to you that there's very high potential for this possible energy generation method. Cons are a little trickier. Currently, it has negative net energy. We have working hydrogen fuel cells. The issue is that they're really small, and we need to spend a ton of energy creating hydrogen gas. Hydrogen gas is actually not naturally occurring in high enough quantities. We find hydrogen atoms as part of larger molecules, and so we need to create hydrogen gas. And there's two different ways to do that. We can split apart water, or we can split methane. If we're splitting methane, we're going to be creating actually carbon dioxide emissions in that process. It's very expensive to generate this hydrogen gas through either of these methods. It's also pretty expensive to make the equipment for the fuel cell. It's a new technology. There are research and development costs. The scale of the technology is low, which makes it more expensive. And the raw materials to build these cells include platinum and other rare earth metals that are used as catalysts. Think about the mining that has to happen to get those rare earth metals. Hydrogen gas is also highly combustible. If you've heard of the Hindenburg explosion, that was a blimp filled with hydrogen gas that essentially blew up over Lakehurst, New Jersey. It's very, very combustible. Next section. Oh, we're done with the different non-renewable energy sources. We're at the end. Energy inefficiency. Bad news. About 84% of all commercial energy in the US is wasted. Okay, so here's all of our energy inputs, our non-renewable fossil fuels, our non-renewable nuclear, hydropower, geothermal, wind, solar, and biomass. So we've got chemical energy, we've got a little bit of kinetic energy. We put that into the system. What do we get out? About 9% of that turns into useful energy, specifically electricity. About 41% of it is unavoidable energy waste because of the second law of thermodynamics. And about 43% of that is unusable energy because of inefficient power plants, inefficient electric devices, or leaky, poorly insulated buildings. The four most wasteful things in our society right now are the incandescent light bulb, where 90 to 95% of electricity is lost as heat, not transformed into light energy. The nuclear power plant, where about 92% of energy in nuclear fuel is wasted when we consider the entire nuclear fuel life cycle. So this is why we say nuclear has very, very, very low net energy. Only about 8% of the chemical energy in nuclear fuel rods is ever transformed into electricity when we take into account the massive amount of energy that goes into building, running, operating these power plants, refining our uranium, etc. The internal combustion engine in most cars. These are really inefficient. About 80% of the fuel energy is wasted and is not converted into kinetic energy to move the car. And finally, coal-fired power plants. About 75 to 80% of the energy in coal is wasted in the power plant when we include the energy required in coal mining, production, and cleanup. So there are some solutions. Cogeneration is one of them. Cogeneration is when a fuel source is used to generate both useful heat and electricity. So take a look at our diagram. You'll see CHP. This CHP stands for combined heat and power. And this might improve the efficiency of power plants to 75 or even 90%. So here, all of that steam that's generated in our power plant, that steam and hot water can be used for heating and cooling. And that's really the basis of a combined heat and power system. We're boiling that water, we're using it to generate electricity, and then instead of just getting rid of that hot water or recycling it back to the boiler, we can actually use the leftover heat to heat the building that we're in. Denmark is the world leader in cogeneration, and they get about 82% of their electricity from combined heat and power systems. Energy conservation at home. What should we do? I'd actually encourage you to pause the video and really look at this image. There's a number of techniques that should be used in any home to increase energy efficiency. Some things include adjusting the thermostat lower in the winter, a little higher in the summer. Using energy efficient appliances. If it has an Energy Star rating, that's a good sign. That means it uses less energy than older models. Conserving water. There's a lot of energy that's required to move the water to your house to purify the water in the first place. So using less water is an energy conservation technique. Conservation landscaping that reduces water usage is also important, but you can also plant trees to provide that shade so that in the summer your house doesn't get as hot and you don't need to use as much energy for cooling. Using LEDs instead of incandescent bulbs. Remember, get rid of those incandescent bulbs. They're super inefficient. Energy conservation and transportation. Well, fuel economy standards, or the corporate average fuel economy standards, are something that have been in place since the 80s, and they significantly increased the miles per gallon that most cars in the United States have. However, the United States is actually probably the worst in the world for our average miles per gallon. Most MED, or not the worst, one of the worst MEDCs in the world when it comes to average miles per gallon. Cars in Europe really top our average of 25 miles per gallon. We've got some work to do. Electric vehicles also contribute to higher miles per gallon and are really important for energy conservation and transportation. They're much more efficient than the internal combustion engine and will actually get more bang for our buck. More of the chemical energy will be translated into kinetic energy in electric vehicles than in internal combustion vehicles. The electricity used to power those electric vehicles can and should be renewably sourced. Remember, it doesn't help us so much if the electricity we're using to power our electric vehicles is from a coal-burning power plant. Ride sharing, public transportation, carpooling, those are all important ways to conserve energy in transportation. What about in building design? This is so exciting. This is like the green roof, green building concept. Okay, so we can have passive design elements like this green roof that you can see on this building. Passive solar techniques, building our buildings to take advantage of that solar energy. Moving the thermal mass of the building. This really ties into our passive solar structural components. We're really just trying to keep our buildings cool in the summer, warm in the winter without inputting any extra energy. Insulation will help with that too. Using lighting from the sun, large windows that are shaded at the right angle so that we can take advantage of that light without having it contribute to our heating. And a green roof, which can provide more insulation, can reduce energy costs for heating and cooling. Active technologies would include heating systems powered by geothermal or solar energy and solar panels to provide electricity for the building. All right, the last thing that we're going to mention briefly is energy conservation in the electrical grid. Remember, the electrical grid is the physical system of wires, power lines, transformer stations that link all of the power plants in our country together regionally, nationally, or locally, and distribute electricity to buildings. So right now, we have a very centralized macro power system where we have a few massive power plants that may go offline. Think about what's happening in Texas right now. Energy conservation in the electrical grid means shifting to a decentralized, flexible micropower system that takes advantage of the individual resources of a particular region. Is it a region where we can put solar panels on most of the buildings, so many solar panels that we can actually generate more electricity than those buildings need and then put it back into the electrical grid? Is it a region where we could generate some geothermal electricity and put that into the electrical grid? How do we create a decentralized, small-scale system where residents are generating their own electricity, putting some back into the power grid, and we're not at risk of major electrical grid failure if, say, a couple power plants go down because of a hurricane or a snowstorm. Whew, okay, you made it through. You may need to go back and rewatch some of this. I know there was a ton of info. I hope you enjoyed it, and we'll see you in class in a couple of days. Bye, people.